Hi, AP Physics. In this set of notes, we're going to be learning about rotational inertia, what it does, and how it's different than regular old linear inertia. So, for the first part, we want to look at the net torque. So, the net torque is the sum of all the torques together. And this is also going to be equal to the two components of torque, right? It's going to be the force times the radius. As long as these things are perpendicular, we don't have to have the sine of theta. So let's just say at the moment, all of the forces are perpendicular to these radii. Then I can go even farther, and I can split up force into mass times acceleration, and it's the tangential acceleration that we want to focus on, multiplied by that radius. But here we have the linear acceleration, and since we're rotating, we want the rotational acceleration. So this is defined as acceleration is equal to the radius times alpha. And alpha is the change in omega, or our rotational speed over the change in time. So plugging this into our equation, we get mass times the radius times alpha times radius. We can clean this up just a little bit to have the sum of the mass times the radii squared times alpha. So we have some mass times the radii squared, and then how quickly the rotational speed is changing. And here we get to our answer that this mass times radii squared is our rotational inertia, or what we also call moment of inertia. But before we move on, I want us to see how this is similar to force once again. So off to the right side here, let's move our drawing over. The net torque now can be written out as the inertia multiplied by the rotational acceleration. And this should look very similar to the net force is equal to mass times linear acceleration. So torque really is this counterpart to force, but at the same time, it is different. Rotational inertia isn't just going to be based on the mass, like force is, but it's going to be the mass and the radius squared. Torque is also equal to the rotational acceleration, just like force is proportional to the linear acceleration. The other part of this is that mass is not evenly distributed throughout an object, or it's not always all at the same radii. Some mass is closer in, some mass is farther out, and so this is going to change the moment of inertia as you see on page 261. Depending on the object, the inertia is going to be very, very different. And based on where it's rotating around is also going to be different. So the next part of this is we are going to use some integrals to find the moment of inertia of an object.